Discord on this computer. Okay, so first off, over here on my GitHub page, if you go to GitHub, so if you go to the link GitHub page on Canvas, you click on data structures, you can go ahead and look and see that we've got, you know, all the code that I've done on my computers, but on my computer in the past. But if you go over here into the folder, you'll see on the bottom there's a study guide, which is probably not as extensive as a study guide as some of you have been creating. Let me go ahead and just get it. And basically, because it's just a list of the things that I want you to a list of things to look at. This hasn't been updated since some of the links are dead, like this one. But some of these, so the second and the third are still good, I believe, and the fourth. So these are various final exams that I really liked, and I always go through that, make a point of going through them. So I figured we'll start. I also noticed that there was another Harvard final, I think, in my bookmarks that I had. Final. So this one's 24 pages versus 14 pages. Yeah, so we've got two finals that we can deal with. I think this one is, yeah, there's a bunch of object-oriented programming in here stuff as well, but hey, there's plenty of stuff that's also, yeah, so I haven't looked at this one yet. The second one I pulled up, I've not actually looked at it. So it'll be the first time I'm trying those problems as well. Whereas this one, I've gone over I know the questions pretty well. So we'll be tackling that. All right, and I have one question for everybody. So what happened when I did this? What just happened to the screen?
We see the wallpaper with the wave thingy.
With you see the Hokusai Vaporwave, and now you see a whiteboard?
Yep.
And if I do this, you're back to the final?
Yeah, you're just switching your.
Okay, I wasn't sure if that would. I wasn't sure if the virtual desktop stuff would be compatible with Zoom. I'm glad it is, because that makes it fairly easy. Because, you know, virtual desktops, by the way, you should use it. All right, so exam consists of 3 parts. Bunch of multiple choice questions with 3 point each. Problem 4 is, okay, so pretty much everything else is catching up to I3. Like I'm using something called Power Toys from Microsoft and there's a thing called Fancy Zone for creating your own layouts, which is nice. So to get to this practice final, just go to my GitHub webpage, go to Destruct. So sorry, go to my GitHub, which should be linked on Canvas. Click Destruct for data structures. It's in the study guide PDF. For right now, just don't worry about that. You'll be following along on my screen anyway. So for the multiple choice, I really like their policy. This one's from Harvard. It is, you get 2 answers. So you basically, if you're undetermined, you know, it's 3 points, but if your second answer is the correct one, then you can get credit for it. So let's just go ahead and do this. Let's go ahead and do this over here. So yeah, we'll do this. We'll have it the way it was. All right. So suppose items A, B, C, D, and E are pushed in that order onto initially empty stack S. S is then popped 4 times. Okay, onto an initially empty stack. Sorry. S is then popped 4 times. As each item is popped off, it is inserted into an initially empty queue. So we've got ourselves a stack here, and we got ourselves a queue. Also, I don't know why I just go with this wallpaper. It is just nice and generic, and I like the purple. So, okay. So A, B, C, D, E. So let's pop them. Let's push them in. A, B, C, D. And now, and then E gets pushed and then it is popped 4 times. As each item is popped off, it is inserted into an initially empty queue. So E, D, C, and right. So I'll just write over here, back, and front. Okay. B. Okay, so we've popped off pop 4 things off, insert it into the queue. If we remove 2 items from the queue, okay, how do we remove items from the queue? We remove the front. What is the next item that will be removed from the queue? Well, it will be the thing at the front. So that would be C. So our answer would be C. Any questions on this one? Notice that I did not, that my instinct was basically don't draw this, that my instinct was draw this. Immediately, as soon as they said put things into a queue and figure out what, put things in stacks and queues and figure out what's going where, I picked up my pencil and started drawing. Right, so that is so pencil and paper or whatever equivalent you're using is your best friend here. So you should use it. Because trying to do it in your head is for people who like to lose points. So, all right. So if the binary, and I finished grading half the class. I will finish grading the other half tonight for the second exam. I'm sorry that it's been taking so long for that. I've been busy with life things. The issue with working at home is there's like no work-life balance whatsoever. It's either all work or all life, and it's very tough. All right, so if the binary tree below is printed in pre-order traversal, what would the result be? And so let's go ahead and write. So pre-order means that we want to do our root first, then we want to do our root first, then our left tree, and then our right tree. So this is wrong because root should come first. This is wrong because root should come first. So next we need to, the next thing is that, so root, left tree, then right tree. So root, so 17 should come next. So this is wrong. And then root, but I need to do the whole root, the whole of the left tree, then the whole of the right tree. So, right, do this thing, then this thing, then this thing. And notice that with E, we're kind of, sorry, with D, it says, hey, do the whole left tree. I'm going to do 6, then 17, then 22. And then 9, 4, 16, 12. That's not pre-order, right? We got it for pre-order. We would want to do 6, 17, then 9, then 4. And so this doesn't match at all. So the answer is E. All right, let's get to our first graph question, which is going to be the first graph question you've had to experience, I think. So a graph implementation that uses a 2-dimensional array to represent the edges would be most reasonable for the following cases. A graph with 1,000 nodes, 1,200 edges, 100 nodes, 4,000 edges, 1,000, 10,000, 10, 20, none, since a graph can only be represented by a linked structure. So which of these can we immediately throw out? E, right. So, right, we have 2 ways of encoding a graph. The first is basically this link structure that we are taught, that this link structure, which is basically saying, hey, A is connected to all these nodes. So A is connected to B, C, D. B is connected to, and let's assume these are one-way edges. So A and D, and C goes to D as well. Okay. And then D doesn't have an edge that have a directed edge leading to anything. So this is a linked structure. Whereas, but that's not how we're storing it. We're storing it as a array-based structure. We're basically saying A, B, C, D, A, B, C, D. Here's a grid, right? A badly drawn grid, but hey, you know. Okay, so like we'll put some zeros here to represent the fact that we're going to put some zeros here because, by the way, it is totally kosher to have edges that look like this. So A to B, and then we can have actually, yeah, we can use 0 to represent that an edge doesn't exist. So as you can see here, it is totally kosher to have something like this. It costs 3 to go to myself and then 5 to go over here. So it just is, you're allowed to have an edge that goes to yourself. It's weird sometimes, but whatever. Okay, it's useful in some graph cases. Okay, so like I could say, hey, there's an edge from A to B, and it costs 5 to get there, and then to get from B to C, B to A, it costs 3. So this would encode this relationship. So, okay. So do you remember from my lectures when you want to use one over the other?
Does it have to do with how sparse the graph is?
That is exactly when you want to use it.
But
Yeah, sparsity versus density. And so again, with this kind of case, right? I'll just put ... over here and ... right? Suppose we had a lot of nodes and very few edges, right? Most of these would be empty, useless spaces, right? So if we had a lot of nodes and very few edges, we'd have a very sparse graph. We'd have a graph that looks something like this. Maybe like, this is a fairly sparse graph because like there's around the same nodes as there are the same number of edges. Make sense? That's a sparse graph. And we can kind of see, by the way, from this graph that if there are n nodes implies that there's going to be n squared possible edges. Not that there will be n squared edges, but there will be possible n squared edges. Does that make sense? Right? Because we have n squared spaces. Okay, we have n squared spaces in this grid. That's how many possible edges we have. Make sense? So we have n squared possible edges. So this matrix-based representation, an array for graphs, is much better because, much better for dense graphs, where basically that the number of edges is closer to n squared, where the number of edges is close to the number of vertices squared, basically where we've got more of the spaces filled up. Whereas the linked based structure is much better if we've got a sparse graph, because that one's doesn't have a bunch of empty spaces you need to fill. So our slide, by the way, sorry, not our slides, the trade-off from our textbook, they say that basically that if 25% of all the possible edges are filled, so if we've got 25% of n squared, in other words, for the so if the number of edges is greater than or equal to 25% of, and let me go ahead and let's go ahead and rewrite that a bit more mathematic with the mathematical that we need. Of v squared. So if e squared is greater than or equal to 25% of v squared, I know, not the most mathematical, but it makes sense. Then that's when we want to use an array-based data structure. Okay, so if we've got 1,000 edges and 1,200 nodes, right? So 1,000 edges means how many possible, 1,000 nodes means how many possible edges there are. Well, it would be 1,000 squared, right? Which is, we would just add zeros. So, okay. So the question is, how much of this is this 25% of this? Doesn't look like it, right? That's 12 out of 10,000. That's yes. If it's on your computer, you can use it. So there we go. So A can't be right because this is a very sparse graph. What about 100 nodes and 4,000 edges? So 100 nodes would be how many possible edges? It would be 100 squared, which again, just add zeros if you want to do it like this. So 4,000 out of 10,000, which let's just go ahead and remove those zeros, is equal to 4 out of 10, or basically 40% of all possible edges are filled. So this guy looks correct, but let's go to the other two just to double check. 1,000 nodes, 10,000 edges. Okay, so 1,000 nodes again was and 10,000 edges. So remove those extra zeros. So we've got 10 out of 100. So in other words, 10% of all possible edges filled. So not nearly as good. And then 10 nodes and 20 edges, we can actually do that one in our head since we all know that 10 squared is 100. So that's 20%, which is still below the 25% threshold. So this one is the densest one. So we would go with B. And again, yes, you can use, this is an open everything exam because trying to prevent you from cheating would be a effort in futility. I don't really believe in, I don't know how effective those Proctorio is at against protecting against false positives, which, and I had a friend who got kicked out of his undergraduate degree because of a false positive kind of situation where somebody thought he was cheating and he wasn't.
Did he get to come back in after it was?
No idea. I don't think he did. It was
messed up.
It is messed up. So that's why in those kind of situations, I like to be very sure, and I definitely don't want to automate it. So in that case, I just simply make it so that the final account, I try to account for all this. It's not the greatest. I know we're still teaching under non-ideal situations, but I'm doing the best we can, and I'm just trying to, work on the honor system here. It seems to work out pretty well so far. All right. So let's take a look at this. A binary tree is constructed of nodes of the following class. So, hey, look at that. They didn't do generics. Oh, well. So this just has ints instead of data, whatever. All right. So consider the following method. The mystery method, which takes in a node and returns a node, right? And so it says, hey, if the root.right is equal to null, return root. So otherwise return mystery root.right. So what does this mean? Let's try to put this into English words. So if root.right is equal to null, so in other words, if I don't have a right subtree, return myself. We're done. Okay, that is the base case. No right tree, we're done. Otherwise, I have a right tree, so return this on myself. Which then, if I have a right tree, return mystery on my right subtree. And if I have a right tree, I'll call this on this. And so in other words, this is going to go all the way until I hit so what is this going to do? I'm going to just basically, if I call this on the top of the tree, it will go all the way to the right and return the rightmost node. Does everybody understand that how this is what we are doing? Stupid allergies. So this is going to give us our rightmost node. Okay. So now we consult 3 supposedly tech-savvy consultants, and we get the following opinions about what the method does when pass the method to the root node of a binary tree. Consultant Roman numeral 1 says that it was the last node in order traversal. Consultant 2 says last node in post order. And consultant 3 says it was the last node visited in level order traversal. So which of these opinion is correct, regardless of the way the tree is structured? So let's look about this. So we know that the true answer is it's the rightmost node. So well, let's think about this. In order traversal, no matter what, that's going to be right, because with in order traversal, the last node in an in order traversal is always going to be the rightmost node. If we add a node here, this still will be the last rightmost node, the biggest thing in the list. So that would, sorry, in the tree. So this would be the last thing returned, right? Right. Let's go ahead and fill in the blanks, right? 10, this has to be 7. So this 10 would be the last thing in an order, right? It just has to be. Does everybody follow that? In order means that the biggest thing is in the last position when you print it out. So, and the biggest thing is always the rightmost thing. So 1 is correct. Yeah. Number 2 says returns a last node visited by post order traversal. Okay, he's right under this scenario, right? Where basically the root is the rightmost node. But as soon as we add this, right? Right? As soon as we do this, it would be A, B, C, D, E. We want C to be returned last. So post order would say, do my left subtree, then do my right subtree, and then do myself. And so the last thing in this post order traversal would be A. So B is wrong. Sorry. So number 2 is wrong. The guy, consultant number 2 is just wrong. So number 3 says the last node visited in a level order traversal. What in the world is that? Well, he's just being silly, and he's using a silly name for something you've learned by now, which is breadth first search. Level order traversal is just simply going through the levels in order. I think, I hope. A, B, C, D, E, F, G, right? So level order, right, would go A, then B, C, then, okay, so it would print out the rightmost node in this case, right? All this is breadth first search. But if I, again, remove G from the equation over here, the rightmost node would be C. And now we have a counterexample where we have, where basically would be where the rightmost node is C, but yeah, not really going to work. That's not what we want. Sorry, a level order would say F is the last node. So consultant A is the only one worth consulting on this problem. All right. With a poorly chosen hash function, it is possible to have a situation in which the search time for a hash table of n items goes to anyone? What is an, yeah, O of n. So what is a poorly chosen hash function? Well, let's not overthink it. I'm going to write one right now. H of x, so the hash of x is equal to, ooh, I know, 0. That is a poorly chosen hash function. It's a great example of a poorly chosen hash function. Why? Because everything's going to the same key. It was very easy to write, don't get me wrong, but not very well. So basically the first, so we're always going to have collisions, and the number of collisions we're going to have is equal to the number of items that have already been put in. So yeah, O of n. So a lot of this time, so for a lot of hash functions, we will, sorry, for working with hash tables, we assume that that the previous programmers had spent a lot of time on this problem and figured it out, and so that it does approximate constant time. I don't feel a need to go over number 6 because you already did that on exam 1, or at least the practice for exam 1. But let's go over another hash table problem. So here we go. A police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets. So it can be quickly determined very quickly whether or not a given license plate is in the database. All right. So again, just an aside here, I should point out that every person is a terrible driver here. I'm not saying that basically because you're all computer scientists and computer scientists are bad drivers or something like that. I'm just saying that humans kind of have no, we kind of overestimate the ability of humans to maneuver multi-ton vehicles at high speeds. I'm just saying. And we kind of just like look at the at the human death toll caused by auto accidents, or the economic toll caused by auto accidents is like the cost of doing business. I mean, so much so that you're mandated to have insurance. So because it's assumed that if you're driving, you're going to get into an accident at some point. That is what it comes down to. So yeah, my side there is that driverless cars can't come soon enough. I really think it will make the the world safer, at least in terms of driving. Also, I like driving very long distance to my parents and my in-laws. They live in Georgia, and it is about it is a 700-mile drive from here. We can do it in a day, but it's exhausting. And we generally do it in a day. In the before times. But it would be so much nicer if basically the car could take over most of the driving there. Because interstate driving is fairly easy. You just go straight and avoid the obstacle in front of you.
What do you think about I know people say one of the reasons, my dad, he is kind of not into the driverless cars because he's afraid the car's gonna get hacked or something. But aren't all the cars pretty much run by computers now anyway?
There are a number of functions in the computers there anyway, and that is a concern. It's not like it's not like these companies. I don't know if I do not know how well their security is, and that is a concern. But the answer to that is don't let them take instructions from random things. The only way you should be able to take instructions is from inside the car, and you really there should be limitations there, and it is a very valid concern, I feel, but I don't think that necessarily the average person has anything to worry about there. But it is something that is a concern, and it is a valid concern. But I also think that the concerns over that outweigh basically humans who get tired and make mistakes. And for those of you who aren't from the US is fairly big, and it is kind of mind-boggling how far people will drive in the US. It sounds kind of crazy when you hear it first. Again, from Pennsylvania to Georgia, that's about for me that takes us about 12 to 14 hours worth of driving to go, and that is something that I did, I think, 5 times round trip in a single year. It is so it is kind of, it's just one of those things that is cultural. So a department wants to maintain a database of 1,800 license plate numbers. I certainly hope not. Okay, wants to maintain a database of 1,800 license plate numbers of whether people who frequent tickets, or people who receive frequent tickets, so it could be very quickly determined whether or not the given license plate is in the database. So we have 1,800 license plate numbers. We want to make sure, and we want to quickly look them up. Speed of response is very important. Efficient use of memory is also important, but not as important as the speed of response. So we have 1,800 license plate numbers of people who get frequent tickets, and we want to determine whether or not they are whether or not their license plate is in the database. Which of the following data structure is most appropriate for this task? So speed of response is important, but efficient use of memory is also important. But speed is most important. So a sorted linked list. So let's talk about complexities here. What is the space and what is the time and the space complexity for, hey, given a number, find that number in this sorted linked list. So how long is that going to take? Well, it would take a lot. It would take. So George, you are unfortunately incorrect. That is it is going to take log n if it was an array list, but we're dealing with a linked list here. Linked lists can't do, doing a binary search on a linked list is a losing proposition. Because remember, you takes n to get somewhere in that list. So you're actually better off just kind of going through the linked list in general, because in order to get to indices, you're going to have to manually move back and forth one at a time, whereas as opposed to jumping through them. So sorted linked list is definitely not the way to go, because it takes O of n time to find anything, and it's going to take O of n space. But I mean, everything here is going to kind of take O of n space. But so we'll get into that so let's just find things with the best times. So no to this. So now with a sorted array of 1800 entries. So a sorted array with 1800 entries. What is the amount of time this is going to take? This one will take log of n, because we're dealing with a binary search here, because an array, we can just jump around between the entries. Okay. So actually, in terms of memory efficiency, this is the most memory efficient solution possible, because we have an array, and the array isn't going to take up any extra space. We've got 1800 license plate numbers. We have 1800 entries. Every space is full, no wasted space. We don't have any overhead in terms of pointers. So log n and no extra space. Awesome. So now we come to this part, the bulk of our problem, which is probably one of the correct answers, because we have 3 hash tables. These are all hash tables using open addressing. What does it mean to be a hash table using open addressing? What does that mean? Feel free to drop it in chat or unmute yourself and speak. Yep, exactly. Look for the next thing if the spot is full, right? So we look, open addressing simply says, hey, if my spot is taken, I'm just going to take the next available spot. What is the next available spot? That depends on our definition of next. So a hash table using open addressing with 1800 entries. So this is actually pretty bad. Now, why is that? Well, I always like to use the analogy of a parking lot. And you've probably heard that in the videos, but in case you didn't, right? So suppose you're trying to park your car, right? And you get into a parking lot and you go in and it says 1 space available. How long does it take to find that one spot? Right, we've got 107. We've got our parking lot has 1800 possible spaces. 1799 of them are full. And we're going to get into the situation kind of thing, right? How long does it take to find your spot? Very long? Yeah, pretty long. Yep, so exactly. It takes O of n time. Basically, you effectively have to search for through every single spot to find a spot, unless you get lucky and, you know, somebody just pulled out recently. When you're looking for that last empty spot, it takes forever. Okay, what about something, what if though, here though, it kind of is the same way, just in reverse. If we're looking for our car, e.g. we are given a number and looking for it over here, it still takes around O of n time because the entire thing is full, right? Hash tables work better the emptier they are, right? Same reason, and for the same kind of logic behind looking for an empty space for, you know, to park your car. Or if the parking lot is full and you're trying to find your car, but you didn't remember precisely where you put it. You remember the general area, right? Right? You know you parked on this deck, but oh my God, it's full. And yeah, so it takes forever to find if the parking lot is full. Now let's look at this one. Using 3,600 entries, right? We have 1,800 license plate numbers. We have 3,600 entries. What does that mean? That means that the parking lot in this example is half full. if the parking lot is half full, this is actually one of those kinds of situations where the glass being half empty is better, right? It means the parking lot's half empty, which means half the spaces are open, right? How long does it take to find a spot then? Yeah, it takes, oh, it doesn't even take half the time. It actually takes a constant amount of time. It takes a great, I believe takes, let's see. I got to go and look it up now. Knuth. Let's see. Here we go. That is linear probing. So here, to look for something where, so here we go. The amount of time it takes to insert something is equal to 1/2. This is a theorem that Knuth came up with. For some reason, he decided MS Sans was the great way to go. 1/2, 1. So how many probes do you need? Let alpha be the average length of the list. Basically, this is what we call our load factor, which means that basically n is the number of items we have, n is the number of items we have, m is the amount of how full it is. Take those two. So it would just be this distance. I feel like this is a different equation than we had in the book, but the point being is that this factor, notice that basically it's all dependent on how full your list is. I feel like there's a better, here we go. Performance. I covered it in the videos. I'm just trying to, I just can't remember it off the top of my head. But the I don't think it was a squared anyway. I think it was 1 plus 1 over 1 minus, I think this would have been. So if it's half full, it would take about this average number of steps, which would be 1 plus this. 1 over 2 is equal to 0.5. 1 divided by 0.5 is equal to 2. Average number of steps would take about 3. I'm probably wrong with that in terms of like it might take 2 steps, but the point being is that it's a constant number, is that it on average will take about 2 or 3 kind of steps to find it. Again, I could be wrong about it. I'm just trying to remember the equation. I know that our slides covered it, and the textbook has it, but I am working without the textbook because my textbooks are stuck at school. But the point being is that it takes a ridiculously short amount of time to find it. But we're using double the amount of space that we need to. Actually, hold on. I did have a textbook. I just want to make sure that I tell you the right information and I'm not making stuff up. Because, you know, I'm professional like that. Ah, yes. Okay, so our textbook states that this is the equation. So the expected number of comparisons that you're going to have to do is equal to 1/2 times 1 plus, yeah, I had it except for the 1/2, 1 minus L, where L is the load factor. What does the load factor mean? That means how full is the hash table. So at this point, right, we're looking at 1,800 out of 3,600, right? So we've got 1,800 license plate numbers. We've got 3,600 spaces to put it. So that load factor is 1/2, right? So let's go ahead and replace that. Sorry to spend so long on this one. It was just, I wanted to make sure that I got it right and wasn't just making stuff up, which I forgot the 1/2. Okay. So again, this becomes 1/2. 1 over 1/2 becomes 2. 1 plus 2 is equal to 3. 3 divided by 2 is equal to 1.5. So it takes, okay. So once you find a spot, it takes about, once you get to your spot, you're going to have to do 1 to 2 comparisons on average to find it. Right? It doesn't take too long to find a spot. That's the number of probes you'll have to make on average. Okay. On the other hand, with 10,000, does that speed that up substantially? So again, 1/2, 1 plus 1 over 1 minus, and the load factor here is 1,800 out of 10,000. So we're going to cheat and call it 2,000 out of 10,000, right? Everybody get that right? We've got 1,800 entries, 10,000. We're just going to make the math a bit easier for us. Okay. So that's going to be what? 2 out of 10, which is 1/5, right? So, and the reason is I'm just kind of rounding because we're going to be approximating anyway. So this is going to be 4/5, right? And so 4/5 is equal to, and so now if we do 4/5, that means that this entire thing becomes 5 over 4, which means that this is 9 over 4. I'm going to do that. So what is, so we've got 9 over 4 times 1 over 2, which makes this 9/8 is about the time that's going to take. So it's going to take on average about, because again, we approximated, about 1.125 comparisons. Which, so this one took 1.5 comparisons. This takes 1.125. This is still not that different from each other. All right, so here's the entries we had. So we had speed. So speeds we had n log n. We had n, and then we had these 2 constant factors here. Right, it'll take approximately on average 1.5 steps and 1.125. Make sense? So which one's the best? Well, it says speed is very important, but efficient use of memory is also important. So in this case, it really depends on the professor, but I would go with D because this is constant time, which is about as fast as you can get. And we're not using nearly as much memory as this one, right? This one uses twice as much memory, whereas this one's using like 5 times the amount of memory that we need for, right? Because hash tables perform better the emptier they are. And generally you want to keep your hash table about half empty. Okay. So hopefully I've confused and confuzzled everybody enough on that one. Let's keep going. But also just kind of understand that you didn't need to know the equation to get that one right. You just kind of had to use the parking lot law object. I can demo at the end of this, sure. Okay, so let's go ahead and look. A Huffman tree is constructed for a text document containing 5 characters. We can skip this because Huffman trees aren't something we're covering, but I will tell you that basically number 1 is not a Huffman tree because Huffman trees only have the letters on leaf nodes. And then it says the character E appears most frequently and the I has the next highest frequency. So E should be near the top, not near the bottom. So only 3 could be correct. All right. This one's a heap sort issue, a problem. So, okay. An array of 7 integers is being sorted by the heap sort algorithm. After the initial phase of the algorithm, which is constructing the heap, remember we covered that heap sort is made up of 2 parts. You've got the heapify, which takes n time, and then you've got the n log n heap sort, the actual n log n sorting. After the initial phase of the algorithm, which is constructing the heap, which of the following is a possible ordering for the array? So in other words, after heapifying, not the sorting part, but the heapifying part, which of the following do we want? So basically it's asking, so first off and foremost, when we do heapify, right, what are we doing? We are going to, when we are constructing a max heap, this is not a max heap. The biggest item has to be in the front. And the other thing about a max heap is that basically that we have to have it at the, we have to have, you know, all the subheaps have to be max heap as well. So let's look at this, right? So 85, its children's are, so you can, there's 2 ways to approach this, which is one is draw, which is the more surefire way, or you can use the kind of equations that we covered. 85 is the max heap here. Its children are 78 and 45. 78 and 45. So that seems to out. So what is 78 kids? It's got to be bigger than both of them. Its kids are 51 and 53. It's bigger than both of them. 45, on the other hand, its children are bigger than it. 47 and 49. So that's not it. Let's look at drawing it the other way we can do it. 85. So number B is 85, 49, 78, 45, 47, 51, 53. And again, all you're doing is just simply putting them into a complete tree. So 85, 49, 78, 45, 47, 51, 53. So that seems fine. Let's go and double check though, because I like to be thorough. Okay. So this looks possible. C, 85, 78, 49, 45, 47, 51, 53. And we see that this is not a max heap over here. That part is not a max heap. So C is out. And E, what about E? I can hear the TV downstairs and my kid is playing Looney Tunes or watching Looney Tunes with his mother. Really into Looney Tunes right now. It's very silly. Need to get him back on the educational programming though. 53, 49, 78, 47, and 45. Right. So we have, this is not a max heap because the 53 is bigger and should be on top. So B is our answer here. Let's keep going down. All right. And this binary tree was shown below was constructed by inserting a sequence of items into an empty tree. So in other words, we just entered one at a time, items one at a time. Which of the following inputs would not produce this binary search tree? So let's go through this. 5, 3, 4, that seems fine because 5, then 3, then 4. 9, 12, 7, 8, 6, 20. If you don't understand what it means, just go through the ropes and see if you can identify an issue. So next one, B, 5, 9, 3, 7, 6, 8, 4, right? And that makes sense. All these places, all these nodes are going into the right places. 20, 12, 20. Okay. What about C? 5, 9, 7, 8, 6, 12, 20, 3, 4. Clear. Now, what about this one? 5, 9, 7, 3, 8, 6, 4. Oh, and I missed the 12 earlier, but that's fine. Still fine. 12, 20. Okay. Kind of getting concerned here. 5, 9, 3, 6. Oh, and there's our issue, right? If we do 5, 9, 3, 6, what should happen? The 6 should go over here. So this would not create this tree. So our answer is E. And that's all the multiple choice questions. Now let's get into the interesting stuff. All right. So answers 3 of the 4. So here, these are short answer questions. All right. Suppose the keys on the middle row of a standard keyboard, standard American keyboard, A, S, D, F, G, H, JKL are inserted into succession. We don't really need to cover this one. Basically, what we get is a horrible tree, which looks like this, and I'll just draw it. Really, the next point is creating a 2-3 tree, which is covered in your book, but we didn't really cover it here. Here, again, time constraints. I probably now have the scores down well enough that I could, but I didn't want to add any extra stuff during COVID. Or I'll probably add some, try to go into that stuff during the fall. Did not seem like a good idea to do it during, you know, a point where people are dealing with trying to get vaccines and stuff. So A, S comes after that, then D. So S comes after A, D comes before S, F comes after D, G comes after, H comes after, J, K. Now, hold on a second. Okay, so that jackhammer is not outside the front of my house. It just sounds like it. Is all the CS courses going to be next person in fall? So let me tell you authoritatively, okay, that nobody has any idea what's going on. And let me explain why, okay? First off, nobody wants to commit to anything, right? Nobody wants to basically say X and then things change because variants crop up, okay? And then we have to suddenly change plans. That's super chaotic and super inconvenient, right? So secondly, even if things are kind of like people are getting vaccinated, next we have to, I think the university has to decide, and that's something I'm in favor for, of whether vaccinations are mandatory, right? Do people need to have vaccines before returning to class, right? Anybody who can get one. So if you're medically exempt, sometimes we throw a religious exemption in there. By the way, I'm also aware that is Ramadan coming up? I think it's like, what, tomorrow? Yes.
Yeah, I think it's tonight. Like it starts tonight.
Okay. Well, point being is that I am aware that fasting does occur. So just let me know if you if that, you know, if any considerations need to be made for that. So next is so we have but anyway, so that is a decision that has to be made as well. Again, I'm not on the committees that decide those kind of things. But even if we do like mandate those kind of things, we still have CDC guidelines or adjusted guidelines that say we can only have X number of people in a classroom at a time. So for instance, I know for all my classes are currently scheduled as lecture virtual, but lab in person for both 1060, for both 1051 and data structures. So it's the matter of just getting the spaces as well. That's what kind of makes it an issue. You know, it's subject to change because of all these variants that are cropping up, and making sure that these variants are able to be covered by the current vaccinations. So I don't really know what's going on in the fall other than just, but I do know that it will be easier in the fall if we're vaccinated. If you get your vaccine, yeah, you're still gonna have to wear your mask. to go places. Yeah, it's still not going to be back to normal, but you're going to be able to socialize with people, with your friends, and see them again. You're going to be able to meet up with other students much more comfortably and not have to worry about it nearly as much. Vaccination will change things and make it much easier. Part of what's made the being online so difficult is that so many of us are effectively exiled from each other and only speaking to each other in a virtual manner. Like, despite this, like, for instance, I plan on being on campus during the fall because, you know, at least, you know, parts of during the week, during the days I do have classes, so that I can be there to answer questions in person for students. But I also plan on accommodating for students who don't feel comfortable coming to class quite yet. So it is, so it's a balancing act, but nobody really knows what's going on, except that it's best to assume that we're still going to be having some level of virtualization. So let's go on to this one. So this one will be there will be a question that's very similar to this one on the final exam. Okay. So you are given an empty hash table of size 7. Here we go, like like this is, and I know I'm not. So there we go. We've got size 7 uses open addressing. We've got our sequence of keys to be inserted. So we care about the keys, not the values here. Okay, 15, 17, 8, 23, 3, and 5. Insert these keys using each of the following approaches. If the overflow occurs, say so and indicate the element that causes the overflow. So 15. So let's go ahead. And so we've got our h of x is, so these are using open addressing. And this says the hash code, the hashing is x. So given a key, the index it will end up in is at the key mod 7. And then we resolve using linear probing. This one says it's going to end up at, given the key x, it will end up at x mod 7, resolve conflicts with quadratic probing. So let's go through this. So let's go ahead and also figure out what mod 7 is, so we don't have to repeat the work over here. So what is 15 mod 7? Right, so basically subtract 7 or divide by 7 as many times as you can. And so divide by 7, take the remainder, it's going to be 1. Let's go ahead and figure out these. So we're going to just do this first, since while we're in the kind of mental space of doing modular arithmetic. So 15 will go to index 1, 17 will go to, well, if 15 goes to index 1, 17 will go to 2, 3, right? So, and that makes sense. 17 minus 14 is 3. So 8 mod 7 will be 1. 23 mod 7 will be 2, right? 21, 22, 23. And then 3 mod 7 is actually fairly easy, because if it's number, you know, and remember, n mod other, why? Because I don't like doing n and m, they just sound so horrible, is equal to n if n is less than other, right? That's the easy way to do it, right? So if any number modded by a bigger number is what all I'm saying is equal to itself. So 3 and 5. Okay, so let's go ahead and put these in. So 15 wants to go to index 1. It's empty, so no problem. 17 wants to go into index 3. Empty, it's no problem. 8 wants to go into index 1. We have an issue. Insert, yeah, if an overflow occurs, say so and indicate the element that causes the overflow, which I'll just do by drawing here. So, right, 8 wanted to go into 1, but it couldn't. So it looks for the next available address. So it goes into 2. Makes sense to everybody? Next, 23 wants to go into index 2, but it can't because 8 has impolitely taken its spot. So it looks for the next available spot, which would be 17, sorry, which would be 3, but 17's already taken that spot. So it looks for the next available spot, which is open. So 23. Next, 3 wants to go into index 3, but it can't. Wants to go into 4, but it can't. So it takes the next available spot, which is 5. And then 5 wants to go into index 5, but it can't because 3 is already there. So it looks at the next available spot, which is 6. And so I think this suffice. So this is the way it will end up. I think this suffice. This shows, at least to me, I'd argue that this would show I know what goes where, because you can see, oh, well, 23 was wanted to be here, but actually got there from trying to be in 2. All right. Now let's go ahead and do this, but with quadratic probing instead. So there will be a question like this one exactly on the exam. Okay. So next, let's look at quadratic probing to get a bit more practice. 15 wants to go into space 1. 17 wants to go into space 3. 8 wants to go into space 1. Now this is where it gets a bit trickier. So to look for the next available spot, we want to look 1 squared away. So that just means that 8 will go into 2 like it did before. Okay, now 23 wants to go into 2. It can't. So it looks 1 squared away. But that's empty. Sorry, but that's taken. Next, it's going to look 2 squared away from its initial location, right? Because what's going on over here is that the next spot is that it's basically we're looking at our index plus x until, and we keep incrementing x until we get to another. So we keep looking, to look for a spot, we look at basically index plus a, where a is kind of this offset. So we just keep incrementing a. And so it was 1, 2, 3, 4. But if we are doing quadratic probing, it's a squared. So 1 away from our initial spot. And now we're looking at 4 away from our initial spot. 2, 3. So 2. So 6. So 20. So putting in 23, it tries to go over here. It can't. So it looks 1 away. And then it looks 4 total away. So 1, 2, 3, 4. And that amount, again, is from its initial point. Next, let's go ahead and do 3. Index 3 can't go there, right? And it wants to go into here, but it can't. 17's already there. So it just takes the next available spot, 1 squared away. And then 5 just slides into index 5.
We assume that we'll always be checking down in the list.
Yeah, you're always going to be incrementing up. And if you get to the end, you go, you wrap around, but I think I try to avoid those kind of scenarios. C is double hashing, which basically says, hey, if this first one doesn't work, try this one. All right. Let's go ahead and do, and again, this shouldn't take too long to do if you've studied and stuff, but I'm also trying to explain this as well as tell anecdotes to basically break up the monotony and making sure you can kind of pay attention to this. All right. So let's go ahead and tackle the last one. So graph algorithm. So we've got a graph here. Yay. Okay. So let's go ahead and perform a depth first traversal of the graph shown above, starting with vertex C. Select the smallest edge first when appropriate. So in other words, right, what does that mean? Well, it means that basically that when with C, right, if we're traversing this graph, we have 3 places we can go. We can go to B, we can go to E, we can go to F. Which one should we choose? It says choose the smallest edge first. Smallest edge being the one with the lowest weight. Clear. In the space below, list the vertices in the order they are visited. So we are going to go to C first. And, I could write a data structure, but it's just so useful. I can just draw it over here. So which one are we going to look at next to do a depth first traversal? We can go to B, we can go to E, we can go to F. Well, like I said, we want to select the smallest edge first. So we're going to go to B first. We're at B. So And actually, let's make a stack so that we can keep track of where we are. So C, B. Okay, next, let's look at B. We're at B. Select the smallest edge first when appropriate, but we've already been to C, so we can't select that one. So 13, 17, 18. Which one's the smallest? 13 is the smallest, so we're going to go travel that long, and lo and behold, it leads us to A. So A is the next one visited. A has two edges, 13 and 10. 10 is the smallest one, so we're going to go and follow that one, and it's going to bring us to D. D has two edges, 10 and 17, but we've seen them both. So we're at a dead end. So we are going to pop. Now we're back to A. A has two edges, but we've seen them, but we've seen both the attached nodes. So we're going to pop. Now we're back to B. Now we're back to B. Okay. And at B, we are now have two more. We are connected to 5 nodes. 1, 2, 3, 4, 5, but we've seen 3 of them. So the ones we've not been to, we can go from B to F or B to E, but we want to select this cheapest one. So we're going to go from B to F. And so now CBF. F. Okay. F has 2 nodes to visit. We've been to them both. Pop. We're back to B. Right? And now E, so B has only one choice. So we go to E. E has no nodes we can visit. So we pop. Sorry, put E down here. We pop. B has no other nodes to visit. So we pop. C has no nodes to visit. So we pop. And so we're at our answer. We visited C, then B, then A, then D. Then we went from B to E to F to E. So that's the answer there. All right. So now I'm going to do this. I'm going to put it below here as well so we can see it. But it says perform a breadth first. So now instead of doing a depth first search, we're going to do a breadth first search. Okay. Starting with C. And I'm just going to list them instead of below. I'm going to go ahead and just put them in the space we were just working in. So first thing we see was C. Then do breadth first search. We have to, well, we want to visit B first because, again, cheapest. Then we want to do, so next we want to do E, not E. Well, let's see. So we're at C. So which is the next cheapest nodes to go to? E. Then F. So now, so we've seen C, so we're done with C. Now let's move on to B. B has basically all, B has 5 neighbors. We've seen all these guys, so let's look at these guys. So the next one to visit are A and D. A is the next cheapest. D is the next cheapest. And again, this is kind of this output is also a queue. So I'm just marking when we're done. So we go to A, then we go to D. Next, so we're done with there. Next node to go through is E, but we've been to all its neighbors. Same with F, same with D, A, same with D. Breadth first search is really easy to kind of do. Depth first search kind of takes a bit more, whatchamacallit, organization. All right, now let's go for our final question of the day. We are going to go and look at Dijkstra's algorithm. There will definitely be a Dijkstra's algorithm question on the exam. It is like just an unwritten rule of computer science classes. Doesn't matter if you've learned Dijkstra's algorithm, before. Doesn't matter if it's a senior level class. If you're studying graphs, you're going to be taught Dijkstra's algorithm again, and it will be on an exam again. So just learn it and just relish in all the future classes that you're going to be used. At least that's been my experience. It may differ for you, for Temple. So suppose you're performing Dijkstra's algorithm to find the shortest path from D to E. So we want to start at D. All right. And so we want to find, and all vertices, listing the orders they become known, all vertices to which the shortest path is determined in the process of solving this problem. So in other words, I'm just going to create our nice little graph here. Right, we've got ourselves a couple, so we've got ourselves our nodes. Let me go ahead and actually get an idea here. Whoop. And doesn't have a nice auto move. Let's go ahead and move you here so that we can spread you out. So we're doing Dijkstra's starting from D. I'm just going to do it for the whole thing because that's fine. Okay. And let's go ahead and create ourselves a nice solution. So we've got A, B, C, D, E, and F. So we've got our distance is one of the things we care about, and the predecessor. So to initialize this, right, the distance to D is 0, and its predecessor is itself, or we can just leave it blank. It's fine either way. So okay. And then for everybody else, the distance is infinity. No, sorry, the distance is infinity if we're connected, if we're not connected to D, and then otherwise what it is. So let's look. To get to A from D, it costs 10. And we get there from D. To get to B, it costs 17. And we get there from D. To get to C, it costs infinite amount of energy, and we get there from D. To get to D, that's where we start. To get to E, it costs, again, infinite amount. And to get to F, it costs, again, infinite amount from D. So so now we've initialized our Dijkstras. So now we need to start it. So now we need to go through it. So to go through it, we select the, so we're done with D. So now to go through, we select the shortest, the smallest one. So A is the cheapest cost. So now we kind of use A to figure out, are there any more shortest paths? So we've done. Hold on. Amber alert. Okay. So we've got A. Okay, sorry, that really derailed my train of thought, but that's okay. A is 13. So A, we're going out. So to get the only other thing we can get to from A that we haven't completed yet is to B. So the question is, does 10 plus 13, is that a cheaper cost to get to B? It is not, so we are done. So now we go through again and we say, hey, what is cheapest? What is cheapest for this? And 17 is the cheapest thing left. So now we're going to go at B and we're going to explore all these edges. So it costs 17 to get to B. So now we look at all these edges for coming out from B. B to C is 5. So 17 plus 5, that is smaller than infinity. So let's go ahead and that was weird. So we're going to erase that. And so 17 plus 5 is smaller than infinity. So we're going to put in 22 over here. And we got there from the C from B. Okay. Next. 17 plus 20, 37. For E, is smaller than infinity, 37. And we can get there from B. And now the same for F. B to F, 17 plus 18 is 35. And again, we get there from B. All right, so we're done with B. So now we go through and look for the smallest thing. 22 is the smallest. So we're going to explore, is there anywhere to get cheap to places cheaper through C? So 22 plus 22 is 44. That's not cheaper than the current price of E. 22 plus 30 is 50, is 22 plus 30 is 52, which is more expensive than 35. So going from C doesn't help. D to E. So next, so we're done with E with that. And now actually with E to F, that doesn't introduce any new information. We can't get to anywhere from those. So those are done as well. So this is the shortest path for all those things. All right, so stop share, stop recording.